Let's look at an example that does not have just one solution. So here's an example. Solve this linear system. Of course, until we try it, we don't know how many solutions it has. It could have one, it could have zero, it could have infinitely many. It's a non-homogeneous system. But let's go ahead and solve it. And the way you'd solve it would be to put it into a matrix and then reduce the matrix. And by the way, for section 1.5, I'm totally fine if you want to use technology. I don't feel like for this section that there's any reason to do all the reduction by hand. So feel free to use some sort of technology. If you want to do it by hand, most of them aren't that hard to do by hand either. So totally up to you. So let's take a look at what this solution set actually means and about how to write it down. So we've got x1. Let's get the pen turned on. So we've got x1 minus 3x3 equals 2. And we've got x2 plus 5x3 equals 1, and the last row just says 0 equals 0. And of course we like to have those in a little bit better solution set form. So let's write x1 equals 3x3 plus 2, and x2 equals negative 5x3 plus 1, and x3 just equals x3. This is a perfectly fine way to write the solution. It's not the only way, so we are now going to look at a second way to write the solution. So this is one way to write maybe I should say write the solutions, because there are infinitely many solutions here. But let's get another way. We had the original problem written as just an actual system of equations. We know we have other ways to write it though. And maybe if this had been written in vector form originally, or if we just want to write the answer in vector form. Let's look at the left-hand side as a vector. So I can say the solution vector x1, x2, x3 is equal to, and on the right-hand side, well here, we'll do this step by step. We could say the right-hand side is also a vector. 3x3 plus 2, negative 5x3 plus 1, and x3, and just for the sake of symmetry, I'm going to put plus 0 right there. Of course, that's not very interesting. We didn't really do much. It's a little more interesting, though, when we break this apart and say I could look at this as the sum of two vectors over here. 3x3 minus 5x3 and x3 plus 210. And you can actually go a little bit further with this first vector and just factor the x3 out of it. So you could say that the solution set here is x3 times 3, negative 5, 1, plus 2, 1, 0. This is the vector form. And this one up here that we had before is called the parametric form. The vector form gives us a little bit better idea of a picture of the solutions. Think back to our first example from the previous video. There was just a single solution, right? So these three graphs were the three original individual equations, and the solution set, though, was just a point. It was just this one point in space right here. Now, if we want to talk about the solution set, there are infinitely many solutions, but they are all in the form of a vector, a fixed vector, plus another vector that can be scaled. Graphically, if you think about what that looks like, 2, 1, 0 is 2 over 1 up in 1 up in the y direction and none up in the z direction. There's 2, 1, 0, and then we add to that another vector, and you know how to add vectors, right? It's tip to tail. So we'll add to that, and I can't draw 3, negative 5, 1 very well right here, but just pretend it goes that way. We'll add to that 3, negative 5, 1. So there's one solution point right there, but 3, negative 5, 1 could be multiplied by any scalar, so it could be made longer or shorter, or even flipped around to point the opposite direction, like if we multiplied it by negative 1. So not only are we able to point to that point, but if we make it a little longer, we can point to that point, or a little longer, we can make it point to that point. If we made the green arrow a little shorter, maybe if x3 was 1/2 or 1/3, we can make it smaller, and if we flip it around, and we have an entire line's worth of solution set. Any point on this line going through three-dimensional space will be a solution to the original system of equations, and all those points come from going first out to 2, 1, 0, so from the origin. From the origin, you first go to 2, 1, 0. That kind of gives you a starting point, and then you go any distance in this direction, in the direction 3, negative 5, 1. So you head off that direction, or the opposite of it, as far as you want. That gives you all your solution sets. Okay, let's just compare this before we finish. Compare this to the homogeneous system, the related homogeneous system. So pretend instead of equaling 2, 6, 4, that the system equaled 0, 0, 0. First question, how many solutions is the homogeneous system going to have? And hopefully from the last video you remember that if the non-homogeneous has infinitely many solutions, so will the homogeneous. Those two go together because you're not changing, again, the tilt of those three planes, how they intersect. You can possibly just change what point in space they intersect, or what points, in this case, in space they intersect. But yeah, let's go ahead and take a look at the homogeneous. So I just said let's reduce this with 0, 0, 0 on the end instead of 2, 4, 6 on the end. And of course, the coefficient matrix reduces the same way. We didn't change any of those 9 numbers, so they reduce the same way. And of course, the 0, 0, 0 column still reduces to 0, 0, 0. So let's see if we can describe that solution set now. So the equations would look like x1, let me go back to blue. x1, and I'll go ahead and move this over, equals positive 3, x3 plus 0. I'm not going to bother to write that. I could really need that plus sign there. And x2 equals negative 5, x3, and again, x3 is free, no restrictions on it. So there's the parametric form of the solution, and if we wanted the vector form of the solution, write the variables as a vector, and write what they're equal to as a vector. I'll go ahead and factor the x3 out. And I'll put it over here. And there's no plus. There's no fixed vector this time. I mean, I guess if you really wanted to be explicit, you could say plus 0, 0, 0. That's not necessary. It's kind of like back in beginning algebra, writing the equation of a line. If it's y equals 3x, the slope is 3 and the y-intercept is 0, whether or not you actually write the zeros down. We're basically doing the same thing here. We essentially have a slope and a y-intercept. Before, on the non-homogeneous system, our slope was this 3, negative 5, 1 direction. And the intercept, or the fixed point, was 2, 1, 0. This time we've got a related solution set parallel to the first solution set. It, of course, has this trivial solution. If x3 is 0, you get 0, 0, 0 plus 0, 0, 0. You get the trivial solution of 0, 0, 0, which every homogeneous system has. But there are infinitely many other solutions which start at 0, 0, 0 and go off in this direction 3, negative 5, 1. So all these solution sets right here, if you were to graph them, would start at 0, 0, 0 and go off in the 3, negative 5, 1 direction. Right? So create all these solution sets running parallel to the first solution set. This is always true. The solution to a non-homogeneous system and the solution to the related homogeneous system always run parallel to each other. One's always a shift of the other one. And it's always just this, do you have plus 0, 0, 0 on the end, or do you have the same solutions but with a plus something else on the end that just shifts that solution set, but doesn't tilt the direction of the solution set. I think with that, you are ready to tackle the homework on 1.5, so only 2 videos for this section, so go to it.